Okay, so this is lab 9, and in this we're going to cover the test of equal proportions. So with t-tests, what we look at is the means of two groups. Proportions, though, have some special properties. So whereas a mean can be something that we calculate from 0 to infinity, proportions have a minimum value of 0 and a maximum value of 100. So we have to deal with them in a kind of special way. So like most tests, then this follows the structure of the data. Now the first part of this actual lab 9 script deals with a t-test. So I'm going to scroll down here to uh, line 165, and this is where we're going to deal with this function prop test. Now, proportions are something that we encounter in lots of different sort of real life settings, but we can also construct proportions out of any other kind of continuous data. So the data for this that we've got is actually Donald Trump's tweets. So we've got these from 2009 through to at the bottom of this list, early 2020. And the question we're going to investigate is this one. So are Trump's tweets equally or less likely to get over 50,000 retweets when he does not use mentions? And RH1 then, so this is going to be RH0, our null hypothesis. So this is what we reject when we get when we get under a certain p-value. And RH1, our alternative hypothesis, is that Trump's tweets are more likely to get over 50,000 retweets when he doesn't use mentions. So in this, then we've got figures for retweets, and we've also got a binary variable for whether mentions are used. So just like a t-test, we're going to use a categorical variable, a binary categorical variable, and another variable. But this needs to be a proportion. So the first thing we're going to do is filter by year. And this is actually just going to give us the tweets since 2016. More importantly, though, what we're going to do is we're going to split this variable. So it's at the moment a continuous variable, retweets. And we're going to split it by whether it's greater or less than 50,000. We're using if else to do this. And so this is going to generate a new variable that's going to be called viral, that's coded 1 for over 50,000 and 0 for under 50,000. So I'm going to run that. And if we look back at our data, we're going to see we've now got this variable viral. Now this mostly codes as ones, but we can see some ones here for when retweets is over 50,000. Now, the first thing we're going to do here is we're just going to look at a table. So what we can see is that the number of tweets that use mentions is smaller than the number of tweets that doesn't. So 0 is not using mentions. We've got just over 8,000 of those. And 1 is tweets that do use mentions. We've got 1,900 of those. Likewise, in this viral category, we've only got 120 tweets that are viral and 9,800 that are not viral. Really, though, what we're interested in here is the information we get in a cross table. So here we've got tweets with and without mentions, so 0 and 1, and tweets that were and weren't viral. So out of the tweets that did not use mentions, we have 117 viral tweets. And out of the tweets that did use mentions, we've only got 3 viral tweets. So we can express these as proportions then. And in fact, if we wanted to do this, all we need to do is we can look at this as a proportions table. So if I run this, here are our proportions. So about 1% of tweets without mentions were viral, and a bit less than 1% of tweets that did not use mentions were viral. So we've got some, from the descriptive data, some initial information then that says that it seems quite likely that tweets that didn't use mentions were more viral than tweets that did. The question prop test is going to answer, though, is whether this is statistically significant. Now, this next section then takes you through how we would do this manually. So firstly, we're going to decide on our error level, and we're going to choose 5% for our error level. We'd call this our alpha. And then we go through a series of calculations. So the first 2 things we need are the total n of using mentions and not using mentions. So that's just what we saw in our table here. We're going to call those n1 and n2. What we then need is the proportion of viral tweets within each group. So that's pretty simple. All we need is the sum of viral tweets that don't use mentions and viral tweets that do, and we divide by n1 and n2. And you can see that the results we get from that are exactly the proportions that we saw in this table. Now we then just need to put those together. So firstly, we create what we call a pooled sample proportion. So we use our P1 and N1 and our P2 and N2. We multiply them together and add them up and divide them by the total N. We call this a P-hat. The second thing then is we have a pooled standard error. So standard errors are parts of almost all statistical tests. And in this case, we're using our P-hat figure. So we have P-hat multiplied by 1 minus P-hat, and then Rn again. And this forms our standard error. The final thing then is just that we need to calculate a test statistic. So as we've seen, almost all tests involve a test statistic. And this test statistic is then fed into something which tells us about where we place that on some kind of probability distribution. And in fact, in this case, because of the special properties of proportions, we can actually use the normal distribution here. We don't have to use t like we would with a t-test. So we calculate our z statistic, and that statistic is 4.64. Now, if we remember, that means that a z-score of that is 4.64 standard deviations above the mean. So that's quite a long way above the mean. So we're probably going to get a low p-value from a z statistic that high. And if we want to check that, though, we just have to feed our z statistic into p-norm. And remember that we're interested in whether tweets are more likely to get over 50,000 retweets. And what this means is that it's 1 minus p-norm. If we were interested in less than, we would just use p-norm. And so what we've got here is a very low number. We can see it's very low because this, on the back here, this is the -6th power. So we move this back 6 places, our p-value is essentially 0. Now, is that lower than our alpha? Well, yes, it is. Our alpha is 0.05, and this p-statistic is considerably less than that. Now, again, just like with the manual calculations for our t-tests, we don't need to do all of this every time. This is just to illustrate how the test works through a series of calculations. Instead, what we would use is prop test. Now, the way prop test works is that we think about successes in relation to the overall n. So this is a little bit like our logic for binomial distributions. So we have some successes, in this case, these are our viral tweets or our successes. And then we have an overall number. So if we subtract our successes from our n, that's our failures in this case. So non-viral tweets and viral tweets. And this is the format. So our x is our successes 1 and successes 2, and our n is the group that we draw those first set of successes from, and the group that we draw the second set from. So what are these in this case? Well, as we saw in our table, and we can run this table again here, those numbers are 117, 3, and they're also n1 and n2. And these are the numbers we've got over here. So we could use these objects here to run this test, but I'm actually just going to put in the raw numbers here. So that's 8093 for n1 and 1906 for n2. Now our alternative here is set to greater. So this works the same way t-tests do if we're interested in whether this as a proportion is greater than this. We put in greater. And that's our test result. So here's our proportion 1. This is what we calculated before. P1 over here. And P2 over here. And there's our p-value. So again, exactly the same one we calculated before. So we can complete the same thing with prop test here. Now, one of the difficulties here is what would happen if we swap these numbers around? So let's try 3 and 117 and 1906 and 8093. Now, you can see those proportions there are obviously the same, but our p-value is 1. And that's telling us that this is not greater than this. So the order in which we make these lists also matters here. So we've got to remember that when we say greater, we're saying, is this first pair, 3 and 1906, greater than this second pair? And if we change that to less, we get the same as our original result. So whenever you see this C and then these ordered lists, remember that the order of the list matters too. So in theory, we want greater, but we have to remember that we're saying, is this proportion 3 out of 1906 greater than 117 out of 8093? So actually, this would be the solution we want, but we could also swap the numbers around. So just something to be aware of when we're doing prop tests then, that the order of comparison is defined by the order of these lists. So the last part of this script then just deals with, again, a difference in means. So this is, again, a t-test, and we already looked at this in Lab 8. So we won't look through that now, because this run-through is just designed to look at this test of equal proportions. So next time we're going to look at a chi-squared test, which is somewhat like a prop test, but it could use more than two categories. So I will see you in that one.